Sorry, Kelly, I didn't start until about 7 minutes in. So you missed me explaining why the frictional force on the bottom box is to the right. And trust me when I say that there's not a person in this room who really wants to hear that whole thing again. Trust me. Well, you don't have to trust me. We could take a show of hands. So raise your hand if you're done hearing about why the box feels friction to the right. Is there anybody who needs to hear it again? Okay, so we've covered it. Now, where would you like to go next? Because some of you made other mistakes. So where do we go from here? Ryan? Did I say the force of friction is equal to what? I never said that. I don't think so. I mean, I don't think the force of friction will be equal to that block, but it might be. I never showed that, but I don't think it is. We could look at it if you want to look at that block. They have different masses, though. So, unless they all had the same mass, and even then, I'd have to say the net force would have to be equal to that, but not necessarily anything else. Yes, sir? I'm not understanding how to find normal forces. All right, so the next question was, how do we find the normal forces for the blocks over there? So, so we have block 1 and block 2. Let's address them individually. So block 1 is only in contact with one surface, the block beneath it. So when I consider the frictional force acting on block 1, I'd have to say that there is a normal force upwards from block 2. Is that okay? So this is block 2 on block 1. That's it. That's the only normal force that acts on that block. I mean, there's tension to the right. There's weight downwards, and I believe the weight downwards would have to be equal to that normal force, 2 on 1. But there'd also have to be friction to the left. Now, this friction to the left has caused some consternation. But this friction to the left is the inertia of the box beneath it. It's the fact that something is trying to prevent box 1 from moving to the right, and it's the inertia of box 2. So the force that's trying to prevent box 1 from moving forward is the fact that it does want to slide across the surface of box 2. So the inertia of box 2, the fact that it does not want to move, that's what inertia means. It's resisting the change in velocity. That resistance turns out to cause this frictional force. But it has to be a third law pair. So these two forces have to be equal but opposite. It is that third law force, that friction on box 2 from box 1, that has to be equal to the friction on box 1 from box 2. Now, you asked about the normal forces. So now when I look at box 2, there are more than one normal force. There is the normal force downwards from box 1 on box 2. This is the third law pair between these two forces. And it's this normal force that causes this frictional force. And it's this normal force that causes this frictional force. And they have to have the same mu because it's the same surfaces in contact. That's why the friction has to be the same, because we know the normal forces have to be the same. And they're the same coefficient of frictions. All of those things wrap up together to give us why the frictions are the same and the normal forces are the same. But there's also a normal force from the table upwards. That has to be bigger than this normal force and, of course, the weight of block 2. Because the table has to hold both blocks. So we expect the table to push up with the weight of both blocks. And if we look at the net force in the y direction, that's exactly what we're going to find. Net force in the y direction is 0 on block 2. And there's the normal force in the table minus the normal force of block 1 on block 2 minus the weight of block 2. This has to be true in the y direction for block 2. We never looked at this yesterday, but we're looking at it right now. We did look at this yesterday, that the net force on block 1 in the y direction has to be 0. We did look at that. And that's how we got that the normal force on box 2 from box 1 is equal to m1g. Now, I'm bringing that up because these two forces have to be the same size. So the normal force from the table has to equal n12 plus m2g, which has to be m1g plus m2g. The normal force in the table supports both blocks. That's just the substitution there. But the table doesn't know it's 2 blocks. They just know there's something on there. How's that so far?
Sorry, I normally don't get like tripped up by these, but
it's okay.
I was really confused. Like I was thinking there was a 3m going up on the 1, and then I was wondering where the normal force of the table went, and I thought that it might go to the first block also. Like I was just told, like something clicked, and I just stopped understanding.
That's okay. You're not alone. Look, I looked at a lot of papers last night. You're not alone, which is why I want to have it this way, where we're having a conversation instead of, feeling like you're lost and you're by yourself. Trust me when I say there's a lot of people being quiet right now who I know exactly are having the same problem, but they're just probably just not as able to speak up for themselves. Now, none of this really contributed to the motion of the system because there was no interaction between box 2 and the table. Now, the moment the box has a coefficient of friction with the table, that all changes. And suddenly this normal force is going to play a pretty substantial role. So I make the table rough and not smooth. I put the cart not on the wheels, but on its top. And then there's friction between the cart and the table, and friction between the top block and the bottom block. There's all those frictions now play a role. So, and you have some homework like that. Yes, sir.
How does this question change when the ropes have mass?
The question asked by Xavier was, how does this problem change if the ropes have mass, and how does this problem change if the pulley has mass? We won't really do problems where the rope has mass per se, like with this. We will do plenty of problems where the pulley has mass. The biggest effect of the pulley having mass is the fact that the inertia of the pulley is going to reduce the acceleration of the system. That's the biggest effect. But it's not as obvious as that. It's not like we're going to add its mass to all the other masses, and that's going to be part of the inertia of the system. It's rotational inertia, so the shape of the pulley actually plays a role here. And so our answer is going to involve torque, which is going to produce another type of inertia, and that inertia will factor into the acceleration of the system. It'll be probably some fraction of the mass of the pulley. Hey folks, I need to stop for just a minute, run next door. What I really want to do is so loud. So yeah. What else? What could possibly be next? Oh God, yes.
The fact that we have so many equations, like it's the fact that we haven't dealt with this many equations.
Okay, so Xavier's suggesting that perhaps this is because there's just so many different things, so many different equations, and having difficulty plugging them into stuff. Now that's not unreasonable. I don't really know exactly at this point in time how to tell you to organize yourself. One of the things that I'm noticing on work when I go around and see it is you don't necessarily have a plan on what to do. And if you're watching me, I'm drawing out a picture on the board, and that makes it harder. One of the things you may want to do, and this may or may not help you, but I'm going to see if it does, is consider this for organization. This is not how my brain works. So I would not have jumped to this as a organizational technique. Come on, let me find the corners here and make this get smaller. There we go. So there is 3 separate objects. The motion of the objects are related, but there are 3 separate objects. When you consider how they are related, which direction is the same for all of the objects? Meaning which one links all the objects together? For example, if I labeled this one 1, oh no, that one's I already got 1s and 2s. Let's make this one 3. That's when it's hung. We know that its vertical direction lines up with the horizontal direction of the other 2 objects. So the thing that connects them all together, put on one side of this line. So like box 1, it's experiencing tension minus friction, and it's accelerating. I'm just looking at the stuff that's in the same direction. Box 2, friction equals 3 MA. It's accelerating. The box that's hanging, mg minus tension equals MA. Now, I've linked all the things that are together on one side of the line. Max?
Why is there in the third one? Why is there data? Why is there enough data?
Because that's why I had labeled it yesterday. Is okay if you want me to put M3, I'll put M3 there. What's that? MH for mass hung? Yes. Each one of these is focused on one object. So its equation has to be about one object. So like I said, if you want, if that's throwing us, you said mass hung, so MH. Now, the reason I said bring these together is they have a common variable, and not just one. It's very likely that since this is the part of the system that moves, there will be other common variables, right? Stop worrying about where the nucleus is. I use that just for fun. The nucleus is here. You know, I was just trying to make up a different way to think about it. But look, if you get them all lined up, there could be 100 objects. Add all the equations together. All internal forces will have to cancel out. I mean, look at the right side. I'm just going to add MA plus 3MA plus MHA. So 4MA plus MHA. Just added up all the things on the right side of the equal sign. I'm going to add up all the things on the left side of the equal sign now. T minus F plus F plus MHG, oops, G minus T. Right? This here, this here, that there. Now, if I do that, internal forces are all going to go away. They have to. Friction cancels with friction. Tension cancels with tension. And I'm left with whatever is causing the system to move and how the system moves. No substitution. No worrying about what I plug into what and where am I, and I got interrupted for dinner and now I came back and can't remember where I was. It's a little blind. Be careful. You don't want to throw in one of the equations that's not in this direction, because these are related. Now, there's other stuff going on that's not related to this, like it might cause the friction. It might be related to the friction, but it's not related to the stuff that connects the objects together for how it moves. You know, You know, they might have something to do with the problem, but they're not connected to how the table moves. You might need them later, but they aren't about how the system moves. So if you line up the part about how the system moves together, just add all the equations up. They have to work out like this. Now, this other stuff on the side, we know that it actually has something to do with the problem. There's going to be things like friction. You know, you're going to get this stuff too. You're going to have to be able to deal with that. But that's a little bit later. Did that help you, Xavier? It's not a great organization. It's just a different way to think of it. All right, we have talked this problem into the ground. Really, really talked it into the ground. But is there anything left? I will say, go ahead.
Will you always be able to use this to find the acceleration?
Always is a big question there. But if the system's accelerating and you know the variables that are connected to the acceleration, it is very likely to help. But I don't want to blanket it and say yes, because all this does, this thing we've done right here, and if you want to put this in your notes, this would be the right place to put it. Again, you guys tend to not write down the things that are said. You tend to only write down what I write down. So again, I'm not going to back up, but all this will do is cancel out internal forces for you. What it won't do is handle any external forces that don't cancel out. The moment I introduce friction at the surface, there will be another term here somewhere that's not going to cancel out, because friction on the surface is an external force. It's attempting to slow down both of the boxes that are on the table. That external force will not be canceled out here. This only will cancel out the internal forces, the parts that you substitute because they are acting in equal and opposite directions. You will be left with all of the external forces, things that are a part of the situation, a part of the problem that don't cancel out. Ta-da! Yay. All right. I'm good to do something else. You guys good to do something else? Almost out of time. So I did make a promise and I have to live up to it. Is there anything, anybody needs to bring up a homework question? Because it's due Monday. And I don't have any flexibility on Monday. Is there anybody who can't get started on one or stuck on one? I'm listening.
I've written it twice, so I got a 0 for it, but I couldn't figure that one out.
What does it look like?
I don't know.
Uh,
Does anyone have it pulled up?
I do, kind of. You said it's number.
I believe it's 5.
Okay, 9, 8, 7, 6, 5. Two blocks are attached to opposite ends of a massless rope that goes over a massless, frictionless stationary pulley. One of the blocks with a mass of something or other accelerates downwards a 3/4. Okay. Yeah, I know this question. So it's a standard Atwood machine with a block over here. Oh, not a ball, a block. Block over here and a block over here. And there we go. And it says that mine says one of the blocks with a mass of 5.5 kilogram accelerates downwards at 3/4 G. So 5.5. I'll make this. I know you guys might have a different value, but let's say this one's 5.5 kilograms and it's accelerating downwards with an acceleration of 3/4 G. So let's employ my what I just taught you. So I'm at least being a good steward of knowledge. Terrible teacher, good steward of knowledge. There we go. So I have the forces acting on the 5.5 kilogram box and the forces acting on my unknown box, M. I'm just going to follow through with the way I just did this problem. And I'm going to make this way positive because this is the one that's accelerating downwards. Everybody good with all that? All right. So I'll have 5.5 times G minus tension equals 5.5 times A. Net force equals MA. Questions? T minus unknown weight equals MA. So this is this box right there. Okay, so I've put them all together. So now I'm just going to add the two equations together and get 5.5 plus M all times A equals 5.5 G minus T plus T minus mg. Bye-bye. And now, I mean, you're just going to replace A with 3 force G and solve for M. Does that make sense? Did I assign this question? I'm just curious because sometimes I do and sometimes I don't. And I'm afraid with the way we're having some issues, this one would be fun to see you guys struggle with. Fun is the wrong word, but I did. I don't know either. I like this problem. It was kind of fun. Because I think kids, I think students, I won't say kids, you all are almost adults. I think students kind of see this problem and flip out a little bit. Which one did you, is it pull on the bottom one or the top one? This is a pretty classic question. So there, something like that. I love this question. I just think it's neat. I think kids, have issue with it. And I don't even remember what the question mark part of this one is, because there's so many neat ways to ask this question. Like, what is the minimum force necessary to get the system start to move? Or what is the acceleration of the system under a certain force if it's kinetic? There's lots of neat questions about this one. And it's all you got to do is change where the applied force is, and it just changes the problem enough where you can give this one to one person and this one to the person next to it, and they have completely separate questions. So it's kind of a neat question. So if you have this for homework, enjoy it. It's kind of fun. Keep in mind, there's something about the tension that you have to be monitoring, and that is the tension is the same on both blocks still, even under this circumstance. And a lot of people have a hard time with that. And they also have this hard time with the fact that the one's moving past the other one twice the rate, as if that has something to do with it. It doesn't. Because once it's moving, it's kinetic friction. If it's not moving, it's static friction. And that's all you have to worry about, not how fast they're going. So it's a good question. Work it out. Have fun. So anything else? They'll stuck on something, just can't get forward because, it is Halloween weekend. I want you to have some fun. Not doing anything. Well, I guarantee you can find a way to have more fun than mastering doing almost any other activity. So that's good to know. All right, we're going to shift gears a little bit. How many minutes do I have for the bell rings? About how many? That's enough to do something else. So I don't really have anything more here. I just want you to know that we should be done with dynamics. No matter what situation that's thrown in front of you, it's just some perturbation on these problems. It doesn't mean they won't get harder. But I want you to understand that there's no new material. Now, do you need practice? Yeah. Do you need to have somebody help you with some of them? Sure. But all the problems are going to do is just kind of reshuffle these ideas. Now, yeah, I'm sure if I sit down and really think about it, I can probably come up with something that would just like, make you want to just, bang your head on the wall. That's not the goal here. The goal is for you to see something like this and apply the rules and see what you can come up with. And don't, I don't have to make them complicated. Look, there doesn't have to be friction here for this problem to be interesting. This problem is interesting without friction there. So adding things to the problem just to make them complicated isn't necessary. The idea is to make the problems in such a way that you guys have to think about what's happening, where are the forces, how do Newton's laws apply? So don't think I'm trying to come up with some massive wave, 5 different objects all connected together with lots of cables and pulleys and different kinds of friction. I don't need to do that kind of stuff. Just focus. How does the Newton's laws affect a situation like this? Now, I'm going to turn our attention to something else. It's going to take me about 2 minutes to change where I am. So you guys at home, just chill for a second as I move. And I'm at, Damon, turn the lights on, please. Microphone over here. Unplug that. Change to this. Move the computer a little bit, a little extra slack. Unplug the camera and place it here where I had it last time. It was over here. Okay, can you guys see that? The track okay from your vantage point? Not perfect, but it's gonna, because I only have like 5 minutes, it'll have to do. Yesterday, we were talking about this scenario and the arrangements that we have here and trying to use it to help illustrate the point. One of the things I wanted to do, oh, it's funny, the surface here, whatever they're spraying on it, it's making the surface flake off. So this gets stuck on here now. So, and this is after I've gone over it with Simple Green, which is an organic cleaner, and still it's taking the surface off, and it's slate. So you're sitting on it. I guess so am I. So yesterday, one of the things I was hoping to point out, and it worked out okay, is that we had a situation where we were just barely had enough friction for this to be pulled across the table. And it was just convenient that there wasn't enough for this one. So I didn't plan it that way, but it was really nice that it worked out that way. Now, one of the things that we can do with this is we can flip this problem on its head, and it makes you guys think it's a separate question when it's not. The question I'm talking about is, you could do this the other way, where I give it a push and ask, what's the minimum or maximum amount of tension you can apply to stop it from moving? Do you understand? It's the same question, right? If I give it a push and I pull too hard, I don't stop it. I slow it down, clearly, but I don't stop it. But there's got to be a situation in which I give it a push and I apply enough force to not break the tension and not break the friction too. To not break the tension, to not break the friction and still bring the cars to rest. But there's a ton of little stuff in here. Like I switched to a different coefficient. So it should take me longer to stop it because the force I have to apply also has to be reduced. But then there's questions like, if I do pull this and break friction, how fast will the system be going after the block leaves it? One of the problems that people did have is understanding what direction friction happens to be in these scenarios. And I know we've had some issues even in here with that, but for those of you who don't really believe that the friction is to the right on the box and the table, it should be clear that if I just pull this, you see that the system had to move to the right, which means the friction on that bottom one has to be to the right. Now, this problem becomes the two friction problem, the one where there's friction on the table and a friction between the blocks the moment we just take the cart away. All the cart did besides add inertia was, reduce the friction. So now we've got the possibility of talking about the bottom box having the tension and having friction, or the top box having the tension, but bottom box getting two forces of friction. And putting that into the homework or talking about this as a quiz question, this is the lab. We can sit here and do this. We start adding weights to one side, seeing what it takes to get this to move. We can get the system moving and use it to measure how much friction there possibly is. There's a large variety of possible ways to analyze this particular problem. But I want to point out the range of questions that we have available. And we can test them all right here in the class. What I really wanted to do, though, is I want to do the just plain old boring Newton's second law lab, which is what we're going to attempt to do next week, because we didn't do it this week. So for Monday, what I want you to consider is I want to prove Newton's second law. And we talked about already the fact that we're testing inertia when we add weight to the car. If I'm going to take data in class on Monday, what data would I have to collect in order to measure and show inertia? And how would I know when I've shown it? I'm not asking that arbitrarily. I'm asking that because I would like you guys to dictate to me what we're going to do on Monday. I want to demonstrate inertia. What data should I take and how should I analyze it to know that we've demonstrated it? I'll give you a hint. You have only three things to choose from. F, M, A, because that's where it has to be. So what data will we take and how would we know when we've proved it? All right, that's it for now. But have an answer for me on that on Monday, please. Bye, guys. Have an excellent Thanksgiving. Have an excellent Halloween. Merry Christmas. Happy Easter. Happy Hanukkah. Happy New Year. See you all on Monday.
Have a great summer.
I wish.
Win that turkey like you won last year.
No, I hope not. I don't want to attract any more attention. It just brings me sadness. Bye, guys. See you on Monday.